All right, a 15 by 15 by 5 centimeter piece of wood floats in the water, face down in the water with the water line 3.1 centimeters up the 5 centimeter side. What is its mass? Well, okay, if it's floating, that means that the buoyant force is equal to the weight, right? Right? And so the buoyant force, remember, is rho times the volume, fluid of the fluid times g, right? If that equals mg, well, doesn't that mean that the mass of the water displaced, this is the mass of the water displaced, is equal to the mass of the block of wood, right? So the mass of the water displaced is going to be, mass is going to be density times the volume displaced, right? Density of the water times the volume displaced, right? And the volume displaced is going to be 15, so it's 0.15 times 0.15, and then of course only 3.1 centimeters, right? So times 0.031, right? This is how much is displaced, right? Not the whole block, because the whole block isn't underneath the water, just this, right? Okay, so 0.15 times 0.15 times 0.031. This is an incredibly small volume, so 6.975 times 10 to the minus fourth cubic meters is displaced, right? Okay, so, let's see. And then we want to know, okay, so what's its mass? Okay, we're not quite there yet. Okay, so water, the density of water is 1,000, right? Then we're going to multiply that by 6.975, 10 to the minus fourth, and that's cubic meters, right? Okay, so times 1,000. And we get that the mass of this block is 0.6975 kilograms. That is, I figured out that it displaces that much water, and if it's floating, that must be its own mass, right? An object that has this mass displaces that same mass of water when it floats, right? Okay, so now what is its density? Well, the density of the block is going to be the mass of the block, which we just figured out, right? That's the mass of the block, whoops. Okay, times the, divided by the volume of the block, right? And then remember, this is not the volume of the block, that's the volume displaced. So the volume of the block is equal to 0.15 times 0.15 times 5. Oh, sorry, 0.05. All right, so 0.15 times 0.15 times 0.05 is 0.001125 cubic meters. Okay, so this becomes, the density of this block is its mass, which we figured out, 0.6975 kilograms, right, divided by 0.001125 cubic meters. So these are tricky little problems, right? So this guy divided by this guy, and I get 620. 620 kilograms per cubic meter. Now, if you're looking at this and you're going, you just move on, right? But 620 looks something like it's related to this. In fact, if you double this, you get 6.2, right? Is there a relationship there? And there sure as heck is. So whenever you get these things where it's floating up on there, right? Okay, the amount submerged, right? The distance submerged over the total distance, right, is going to be the density of the object divided by the density of the fluid. That always works, right? The amount submerged, so for example, 3.1 is to the 5, if you have one of these dimension things, right, as the density of the object is to the density of the fluid. Try this. 3.1 times 1,000 divided by 5. Hey, that's 620, okay? And we use this. This is actually how hydrometers work, right? If that block of wood sinks all the way down, then it's exactly the same density as the fluid, right? If half of it is submerged, it's half as dense as the fluid. If it's 1/4 submerged, right? This would be like 1/4 submerged. It's 1/4 as dense as the fluid. If it's 2/3 submerged, it's 2/3 of the density of the fluid. If it's 9/10 submerged, it's 9/10 the density of the fluid. So you can, by taking objects of different densities, you can float them in them and the fluid, and you can measure the density of the fluid by how far it sinks into the fluid, as long as it still floats, right? Okay. So that's kind of a fun problem, huh?